This will be a short presentation, and compared to the beautiful lectures that we listened to during the last 2 or 3 days, this is a very simple and application one. And people who were also in ECMWF 2 weeks ago could clearly recognize the same presentation. It is a practical application. Then, okay, everything started long time ago, 30 years ago, when ECMWF started with a T213 model, and with about 95 kilometer resolution. And we were using then wind for application in the Adriatic Sea, east of Italy. We had immediately a strong problem because wave height were strongly underestimated. Of course, we were worried about the newly born WOM model, but luckily we have also scatterometer. And we could see that the problem was with scatterometer, and the wind speed were strongly underestimated. And once we had the correct wind speed, and we correct according to the scatterometer data, we got some correct wave height result. This was a paper that we published at the time on the problem. On the left, you see our first wave height result versus a buoy that was moored in the Adriatic Sea. And on the right, you see after the correction of the wind. I stress we correct the wind to get the correct wind, not to get the correct data. And this was the starting point. And perhaps many people can wonder what they are looking at in this way. And this explanation why the wind were underestimated, because this is the orography of the Mediterranean Sea at the time. Because what you see here, it is on the center, the highest are the Alps. The two mountain chains following down are the Italian Apennines and the Dinaric Alps. In the center, you see Corsica on the left, where you are now. And so in this condition, this is Corsica, where you are now, of course. So it is not difficult to understand why wind were underestimated. In any case, in due time, with progressive increase of the computer power and so the resolution of the meteorological model, the resolution improved from about 100 to the present 9 kilometer resolution. And turned out the wind were better and better. And the correction factor that was each time evaluated against scatterometer decreased. Still, even nowadays, we are forced with a 16% correction. And that there's something better can be done. Alvise Benetazzo is present at the meeting, could explain what has been done, but we are still talking about the calibration of the wind speed. The point is that, okay, this was the stage where we were, and we realized also that if you compare model wave height versus altimeter, you realize that this was a very early, about 30 years ago, diagram to show that the actual error and underestimate of the wave height depending on the fetch. With fetch, we mean the distance run by wind on the water before reaching the measurement point. So the question, following a big storm in 2018, it was the one when the Dolomite we had 200 kilometers an hour. And we set up with a 3-month study comparison. We organized a 3-month study, including ECMWF UK Met Office, and we also tried to involve NSEP, but there was no reaction. In any case, we had a 3-month long-term comparison of the wind, measuring the wind speed by scatterometer within 200 kilometer distance from the coast when the wind was blowing from the coast. And we tried to relate this underestimate to the called fetch. And this is the basic result that we came across. take the blue line only the reference one. What you see horizontally is the fetch, the distance from the coast where you measure the wind. And this is the one means when the model is similar to the scatterometer wave height. Don't take this as a growing wind speed along the fetch, because the wind speed is growing, of course, from the coast to the fetch, but this curve represents the underestimate with respect to the scatterometer data. Therefore, the model wind speed close to the coast are really, really low. And so basically the underestimate is of the order of 15–20%. Catching up with the scatterometer only after 100–200 kilometers. UK Met Office wind are slightly higher, but still varying with the distance from the coast. And of course, we compare a stable and unstable condition. A stable condition leads to lower wave height. But that's where we focused, because during the fall, the 3 months, October, November, December, of course, most of the wind wave conditions were unstable conditions. So the first question, why does it take so long for model wind to reach the correct value? So basically, it is a problem that the model, we know that present ECMWF model in the ocean are very good. Basically, they fit completely the scatterometer value. Why are they so low? The reply is given here. This is a bit complicated, but the upper, this curve are the ECMWF result underestimate respect to the ideal value here. And this is the same curve ECMWF for ERA 5. We could not show here the 18-kilometer resolution because at the time they were not, the forecast was not archived. What happened is that instead of the fetch evaluating as a kilometer, as here, we evaluate according to the number of grid steps. And in this case, the two curve of the ERA 5 and of the high model resolution fit. So the reply is the following. Resolution matters. The key point is not the distance run, but the number of grid steps. Practically, the message is that each model, whichever the resolution, take a number of grid steps from the coast towards the ocean to reach the correct value. The discussion that we had with people at ECMWF, of course, this paper has been published in the JGR about a month ago by Cavaleri et al. And the key point that the sharp discontinuity that is as a cost cannot be handled is a single step by the meteorological model. The discontinuity are important. As the discontinuity it is distributed along a certain number of points. The second question is that why are the winds so low when they enter the sea? This is the second point. And here we go, we have to look on something on land. We considered a certain number of points that you see with a number around the coast of the Mediterranean. The coast of the Mediterranean is basically mountain everywhere, except, of course, here on the Sahara coast. And we compare the underestimate that is represented in the lower diagram, 4%, 8%, 20%, versus what you can call a parameter that represents the complication of the orography, how rough or complicated, how high, if it is smooth or not. And you see that there is a clear dependence. Basically, the rougher the orography, the more complicated the orography is, the higher the underestimate. These 2 points, that of course everyone has already spotted how come, they are connected to the northwest wind here in the Gulf of Lyon and to Bora here on the Adriatic Sea. And these are problems connected to valleys. These are valley wind where the roughness is relatively smooth because the valley is long. But what is wrong in the model is the transversal dimension of the valley. This is a different problem. Anyhow, the main message is that the rougher the orography, the lower the wind speed when it enters the sea. The second question, for the roughness matter, the rougher the orography, the higher the underestimated. And a good, the final message is the following. This is a one field, of course. Here it is. This is a Rhone Valley, of course, a section, and a Bora section. We have 4 points, 2 on land and 2 on the coast. And in the next one, on the left, take the upper diagram. This is a vertical section of the atmosphere. And you see the wind blowing downhill before reaching the coast. And you see, and on the right, on contrary, you see the temperature. You see the importance of the gravity wave. This the second line of diagram has been obtained, cancelling completely the roughness of the surface on the continent. This derives from a sequence of tests that were done at ECMWF by our Japanese co-author of the paper. And you see the key point is that as soon as you decrease the roughness on the surface and also the wind speed increase, of course. Finally, this is the vertical section of the wind speed as a 4 point. These 2 on land, these 2 on the sea. And you see immediately how close to the surface the wind speed is expected is lowered down by the surface roughness, if you want, and higher speed. Then it's approaching the coast is closer to the lower altitude. The wind speed increase, and this is I find very interesting, is the fact that when you enter the sea, the wind speed, the wind speed is high at about 500-meter height, much lower as the surface, but with progressing distance at about 150 kilometer fetch, there is a mixture. There is a mixture between among the different atmospheric layer, with a decrease of the upper layer, a transfer of energy to the surface. And this is what makes, in the diagram seen before, the wind speed of the model increase with the fetch, of course, till when at 200 kilometer distance, finally we reach the correct value. So the take-home message is that we know that the 10-meter wind is too weak at coastal point. Also, the UK model, ECMWF, is a stronger problem. It takes about between 4 and 8 grid points to reach the correct value, of course. The roughness of land is a lot higher than over the sea. There are at least 2 or 3 order of magnitude of roughness higher on land with respect to the sea. Therefore, the sea, and this is correct, it takes a certain time to reach to develop the new boundary, surface boundary layer of the sea. But this in nature take about 10, 20 kilometers. But because we smooth this discontinuity over a number of 4 to 8 grid points, practically the model takes between 100 to 200 kilometers to reach the correct value. Of course, the last sentence, subgrid orography, how the drag a slow wind even further. And therefore, this makes the sea transition more pronounced in area with evident coastal orography. In fact, when we test some storm coming from the Sahara Desert entering the Mediterranean, the model wind speed close to the coast were almost correct. So orography plays a strong role, but of course, all this is part of all the trade-offs that the meteorological modeling has to do to get the correct forecast and everything else. So this is the play. And the future solution, this was discussed already for the first time 15 or 20 years ago with Philippe Bougeot, who was the head of research at the time, and he pointed out that the only solution was increase the Moser resolution. It was an intuition. Basically, you need the number of grid steps. I don't know, it's not my work, but it should be meteorological modeling, physical downscaling, and I wonder if, talking about the present very popular subject, statistical downscaling, artificial intelligence can play a role into this. In any case, we have a problem with the wind, and this is what we have to live in, and presently the only solution to increase the resolution of the model. Thank you. That's a talk.